All right. So welcome everyone to this uh, episode of the Autonomous Seminars. So today we have Sebastian with us, and he's a PhD student with Josip Grabocka at only Freiburg. Josip is not in Freiburg anymore. He's a professor in Nuremberg, but Sebastian is still a PhD student in Freiburg. And so he's going to speak about his iClear paper, which you're going to present as an oral, right, Sebastian?
Yeah.
And basically the title is Quick to Learning, which we train model to fine tune and how. So I'm very excited to hear about this. So yeah, the floor is all yours, Sebastian.
Thank you, Albert. So, welcome to the presentation on QuickTune. Thank you for coming. So this is a joint work between me, Sebastian, and Fabio Ferreira, Arlene Cadra, Professor Frank Huta, and Professor Joseph Kaboska. So before starting this, we need to motivate this, and we can see nowadays that the communities release many models, many pre-trained models. Like, for example, Hugging Face has more than 400,000 models available, but there are also other model hubs like PyTorch Hub, TensorFlow Hub, even Team Library. So they have different models that offer different capabilities, different modalities, also with different inductive biases. And the problem that many practitioners face is how can I select the model, and what is the best model that I should use for a specific case. And this is a problem or a challenge because there is not a one-fits-all model, right? So if we consider different setups like different metrics or different dataset sizes, even different computer requirements or time requirements, we will have always a different model that might be better for us. And just as a quick example for the motivation, what we did is we selected a set of 24 models, and for all of them, we selected some hyperparameters, the best hyperparameters out of a random search. And then in this figure, we plot the rank of the best model per dataset, per group of datasets. And what we can see from these ranks out of models where we have selected the best hyperparameters using random search, what we can see is that there is not a pattern about a model that is really good on all the datasets and also that is like the best to select by default. And also very interesting is to see that the models that are below, they are the small models, so they also are competitive. So we can see that the ones that have lower rank, this it means close to 0 to 1, they are the best depending on the data set, and we can see that there are even small models that are very competitive. So this is an interesting insight that tells us, okay, maybe we sometimes can use a small model to trade off the time and efficiency. But even after selecting a model, we will have the problem to select the hyperparameters. And specifically in fine-tuning, hyperparameters is very important if we want to leverage the best of the pre-trained model. There are also many, not only the hyperparameters like learning rate or weight decay, but there are also other fine-tuning strategies that include new hyperparameters like co-tuning, SP regularization, stochastic norm, layer freezing. So there are many, there is a huge literature work on different strategies for fine-tuning. And when we select a model, we also need to select what strategy we want to use. A recent work previous work also showed that the hyperparameters are especially important for fine-tuning because, for example, if our target task or upstream task is similar to the downstream to the upstream task or the pre-training task, then we might need a similar learning rate. So all these factors might affect what are the best hyperparameters to use, and we also need to tune them. One example of fine-tuning strategy that is by far the most known is basically fine-tuning just the top K layers and freezing the rest of the network. This is 10 years ago, there was a paper that showed that it was the case that sometimes just fine-tuning the last layer or the last K layers is enough. But actually, it depends on the task. So follow-up work showed that if the task is similar, then only the last layer is enough. If the new task is similar to the pre-trained tasks, then only the last layer is enough. But otherwise, we might need to fine-tune more layers. So this is still a decision problem to select what is the K, the K or the K layers that we want to fine-tune. And moreover, we can see here that also the value of K will affect the memory requirements and time, because if we fine-tune on the last layer, it will take less memory and less time than fine-tuning more layers. Another strategy is called co-tuning. This is a very interesting strategy that basically what they do is that they create two heads, two linear heads, but then one head outputs the target class. So we have the target task, and then the target task have target classes, and then this head H will output those ones. But it turns out that we can also use another label, and what they do is that they take the label of the target class, let's say it's tiger, and they translate this label or this class into a combination of classes from the pre-trained or source task. So if we have different classes, let's say that we're pre-training ImageNet, and then our target task has a class that is tiger, then we can say, okay, tiger is a new, is basically 30% beer and 60% cat and so on. And then we basically create a new label that we can use to fine tune as well. So we will have two heads, one that is using the original label and the other one that is using the translated label from using the original pre-training classes. And then when fine tuning, we will use these loss functions that using both labels. And this is what is called co-tuning. But as we can see here is that there is additional hyperparameters, because this is a new regularization term or a new term that we have to wait for this loss function. And also it adds new memory and time requirements. So every new hyperparameter, most of the times will add new requirements in this case. So we have some challenges. We have a lot of models and hyperparameters that then demand different time and memory requirements. And moreover, there is not a clear consensus of what is the perfect set of hyperparameters to use. Like, there is not a clear picture that we should use or a clear approach that we can always use by default and then get the best. So there are a lot of options, a lot of fine-tuning strategies that we might need to choose and tune. However, we know that, and there are also opportunities, we know that fine-tuning is faster than training, especially if the downstream task or source task is similar to the upstream task or the source task. So if this downstream task is similar to the upstream one, then it will be faster, and we will need different hyperparameters if in case it's otherwise, right? Also, we have seen in the previous slides that small models are sometimes very good enough, and moreover, they can be informative about the performance of other models. So it might be interesting to analyze the interactions among them. So now we are set to the question, how can we actually select quickly the model and the hyperparameters or efficiently? So previous work had two main approaches. One approach is, for example, to use a model selection measure or transferability measure that basically rates, using a score, rates how good a model fits or a pre-trained model transferred to a new task. It's using the dataset and all the task information to do that, and basically it outputs a score that selects or gives a transferability metric about how good the model is to be transferred. Another option, and this one is not using hyperparameters, so another option is actually to do a combination of hyperparameter and models, and then outputs a score that says how good a specific model is for a specific task. And in this case, we can use dataset meta features. And this is previous work that is called zero-shot AutoML that is using these scores to rank the different models and then select the one that is better for a specific task. So in our work, what we are doing is a bit more like we are applying different strategies. We are applying gray box optimization because we know that early iterations are correlated with the performance in later iterations. And also this is more like common in fine tuning, where within few epochs, we already know what pre-trained model is actually promising. And we also add a cost awareness component because, as we have discussed, time is critical, and model hubs include different architectures, and different architectures might need different time for pre-training, for fine-tuning. And also different fine-tuning strategies might need different time and memory requirements. So that's why we need cost awareness. And we also apply transfer SPO because, as we also previously discussed, when we have similar tasks, for example, the tasks are similar to the pre-training tasks, then we might need a small learning rate. If it's not the case, then we might need a larger learning rate. So the task similarity plays an important role, and therefore transfer SPO might be relevant. So as a quick intuition about why the cost sensitive or cost awareness is important, we show in this slide. For example, if we have 3 pipelines and we want to do black box optimization, then as we know, we have to basically tune all of them, let's say 6 epochs, and then all the time that we need for fine-tuning the 3 models will be like our cost. But then if we apply gray box optimization, then we can basically drop some pipelines that are not promising, and then just keep the ones that have the lower loss, right? And this will be, in terms of cost, will be faster, but still there is some problems, especially in the model hubs. It might be the case that this architecture or the specific model has, for example, is very large, and therefore only performing 1 epoch is very expensive. And then what we might actually want is to take into account also the time for fine-tuning this model per epoch. So in that case, what we will do is basically trade off the time, and then choose, instead of the most expensive model, choose a lighter model that still achieves a very good performance. And then like this, we are trading off performance for efficiency, but the loss in performance is very small, and the efficiency is increased, or the time efficiency is increased. And so now in our work in QuickTune, we have 2 main parts. First, we created a meta-dataset. First, we designed a search space and the fine-tuning pipeline, and then we generated the metadata given this pipeline. And also, we propose an algorithm, and we perform empirical evaluation on this algorithm using the metadata set. So for the search space, first we want to clarify. So we call pipeline the mixture or the combination of hyperparameters and model. And then for the pipeline search space, basically we take into account many of the hyperparameters that Team Library already has, like optimizers, learning rate, some regularization techniques. And moreover, we also add, because by default Team Library doesn't have that, we add additional fine-tuning strategies like co-tuning, layer freezing, SP regularization, and so on. And then at the end, we end up basically with 3 groups of hyperparameters. One is fine-tuning strategies. We have 8 hyperparameters there. Then we also have regularization techniques, that is 12 hyperparameters, and some optimization-related hyperparameters like learning rate, scheduler, and so on. And then they make up around 18 hyperparameters. And moreover, for the model side, we select 24 models, that they are the most efficient, and I will explain this in the next slide. So as we can see, we have a somewhat large search space, and then we also need to account for this when we are optimizing the hyperparameters. So as I say, for selecting the models, we selected only 24 models out of more than 700 models that Team Library has. So as I say, we are using the Team Library pipeline and reusing many of the hyperparameters, and we selected, as I said, only 24 models out of 700. And we did this because we wanted efficient models. And then for doing this, we basically account for the number of parameters per model and the accuracy in ImageNet. And then what we want is to minimize the number of parameters, but also at the same time we want to have a large or a high accuracy. So this is basically a multi-objective problem that we solve. And then when we do this, we found that there in the Pareto front of this multi-objective problem, there are 24 models, that they are the most efficient ones. And then those are the ones that we selected for our experiments and for all the setup. And also a clarification. So this was done in a version from Team Library from the past year. So they are constantly adding new models. So it might be that the Pareto front will slightly look different, but we don't think there will be a large change. So once we selected this group of models, we created or generated learning curves by fine-tuning models on meta-album datasets. So for the meta-album datasets, they have 3 groups or versions that they call micro, mini, and extended. And in total, we account for 86 datasets. And since the search space is so large, when we were creating the learning curves, we actually didn't evaluate exhaustively, but we sampled randomly configurations. And then for every configuration, or for every pipeline configuration, we ran a single GPU and up to 50 epochs. Actually, normally in previous work for fine-tuning, 5 to 10 epochs sometimes is enough, but we wanted to have more epochs. And also we limited the runtime of the learning curves. So besides the limit of epochs, if, for example, a specific pipeline in micro takes more than 1 hour, then we stop the execution. So we had different runtimes depending on the group or the dataset group. For example, for micro, we have 1 hour. For mini, we have 4 hours. And for extended, we have 16 hours per pipeline, and also per configuration. And so once a configuration reaches these limits, even if they don't reach the 50 epochs, then we stop the execution of the pipeline. So after we do this, we obtain, as I say, we have 86 tasks, and we obtain more than 20,000 learning curves. In total, we observed more than 700,000 epochs, and we use around 20,000 GPU hours in total for generating this. And as we can see in the table below, the amount of time per dataset changes because, of course, the extended dataset has the largest datasets, while the micro dataset or the micro metadataset has less datasets that are smaller. So fine-tuning extended dataset is more expensive. So now we want to give a quick overview on our method. Basically, our method relies on 2 main components. First is a metalearn cost predictor and a metalearn loss or performance predictor, and there are the input to a Gray-Boss optimization loop. And the input for the metalearn loss and cost predictor is basically the dataset meta features, pipeline encoding, and the epoch or the budget that we are using. So here we have like a overview of the algorithm, but basically we can summarize this in three parts. First, we update the predictors, parameters using the negative log likelihood for the performance predictor and the mean square error for the cost predictor. And then we select the pipeline using an acquisition function that I will explain in the next slides. And then we update the history. So it's a simple group of steps. And then for the acquisition function, we basically have an acquisition function that traces off the performance and the cost. So for the performance, we have basically an expected improvement that is relative to the next query budget. So this is actually based on previous work from 2022, that is referenced below. And basically, the incumbent is relative to the query budget, and it changes depending on the pipeline. And then we trade off this. So in the denominator, we have the cost of fine-tuning the pipeline until the next query budget. So the concept of query budget is important in this formulation. Basically, assuming that we want to do steps of in our Graybus optimization, we just want to fine-tune delta T epochs. And then our next query budget is basically we take the current pipeline, the learning curve, we see how many epochs we have fine-tuned, and then we add this delta T. In the most simple case, delta T is 1, so basically the next query budget is basically how many epochs I fine-tune my model, and then add 1 to this value. And the incumbent that is relative to the query budget, as I say. So if my specific model has the next query point is 2 or 3, then we just need to look up the value of the learning curves that are in the same query budget in this budget. And I will give a specific example here to dip a bit on this idea. So let's assume that we have 3 learning curves and for 3 different pipelines. And so the pipeline X1, pipeline X2, pipeline X3, and then let's assume also that our delta T is 1. It means that we are observing every learning curve only one step at a time, or only one epoch. And then since we have observed 2 epochs from the pipeline 1, then our tau for pipeline 1 will be 3, because that's actually the next query point for this pipeline. For the pipeline 2, since we have observed only 1 epoch, then the tau 2x2 will be 2, and the same for the pipeline x3, then the tau will be actually 3, because we have observed 2, and then plus delta 1 is 3. And then for our pipeline X2, and this is what I mentioned about the relative incumbent. So the incumbent is not the best pipeline or the best performance so far, but it's just the best performance that we have observed for the next query point. So for a specific pipeline X2, then the tau X2 is 2. So what we do is just we observe. In this case, it's just these 2 values, but if we have more learning curves, then we will have more values. But we observe the minimum value only for the epochs that are equal to tau X2. And in this case, then it's this value, and this is our relative incumbent. And as I said, this depends on the pipeline. And then since this is the relative incumbent, then this relative incumbent will basically be used for computing the expected improvement. And then it will change depending on the pipeline. And the expected improvement is using the output of the predictor, the loss predictor, that is probabilistic, and as we mentioned. And so the predictor, as I say, is probabilistic, and what we apply is basically a deep kernel. And this is very useful, especially because we have a large search space. As I explained before, we have around 32 hyperparameters. We have 22 models, 24 models, and the GP, the deep kernel GP, allow us to embed all these hyperparameters in a lower dimension and then use this lower dimension as input for the GP. And basically, this embedding is using an MLP, but also before concatenating all the information, we apply some linear layers. So the information that we concatenate are the hyperparameters, the model, and the one-hot encoding of the model, dataset meta features, like dataset size, number of classes, and the loss curve, and the tau x, that means the next query point. But before concatenating all these values, we pass this through a linear layer, because previous work also showed that this gives an advantage during the training. And then after concatenating, we pass this through an MLP. And this MLP will give us as output an embedding that is used for the GP. And this is what we call the pipeline encoding, that is basically grouping all this pipeline information. So now we want to explain, we want to show the different experiments and the results that we obtain from evaluating empirically our method. So the first experiment is that we wanted to try is what happens if we compare QuickTune to just fine-tuning a model by default, and also with using default hyperparameters. So for this, we selected 3 models that are large. There is a large model that is the BIT, where a medium-sized model, and XCIT, and DLA, that is the smallest model. So basically, they are different size models, and then we just fine-tune them with default hyperparameters. It means we just use the hyperparameters from team library as they are, and if we have fine-tuning strategies, then we use the default values for the fine-tuning strategies. And then after fine-tuning this, we can see, and also given the same budget as for QuickTune, we observe that QuickTune has an advantage, or is outperforming this very simple strategy. So for the budget for QuickTune and for the fine-tuning is the same. For micro, we give 1 hour. For micro, we give 1 hour. For mini, we give 4 hours. And for extended, we gave 16 hours. So the budget for fine-tuning and the budget for QuickTune is the same. And we observe still that of course, this is a very simple strategy, but it's actually a strategy that many practitioners might choose. Just choose a simple model or a default model, and then use the default hyperparameter. So we showcase that using the optimizing the hyperparameters and model is important. Another experiment was to compare this to other optimizers, for this, we compare with ASHA, DEPOP, and DIPAM random search. We can see that QuickTune has an advantage, especially in the early iterations. And we also see that in the extended version, there is a large gap, especially. So we hypothesize that here, all the components like metalearn cost predictor, and metalearn and the metalearn loss predictor are very relevant for achieving performance, especially in the large datasets that we have in the extended version. Another interesting experiment that we performed was basically to select a subset of models from the model hub. So we know that currently the model hub has 24 models, but we were wondering, okay, what happens if we just select a subset of 4, 5, 10, or 15 models, or even only one model, as in the first experiment. So we did that. We selected XIT, DLA, and EfficientNet, and as single models, and we also select subsets of models randomly. So basically, for every task, we sample randomly from the models that are in the Pareto front. We sample 5, 10, 15 models, and then we just run QuickTune on this subset of models. And the general conclusion is using the largest set of models is the best option. So the 24 model experiment was the best. And also using only few models is sometimes only one model, for example, is sometimes not useful, but for micro is useful. So that was an interesting result. For micro using sometimes one model is still useful. But again, this model have hyperparameter tuning. So we are not using default hyperparameter. So even if we use only efficient-net, DLA, or XCIT, we still use hyperparameter tuning. So it still is for micro is a very nice strategy, but still we show that hyperparameter tuning is important. But even more interesting is that for me, an extended, then only using one model is not enough, and even using a subset of models like 5, 10, or 15 is not enough. But still is the best option is to use all the models. And in extended, we can actually, in the extended version of the meta-dataset, we can actually see a stronger pattern where only using one model is definitely not a good option. Using 5 models improves a bit, but using 10 or 15 models is even better. So here in extended, we can see a stronger signal and a stronger evidence that the model size, the size of the model is relevant. Another interesting experiment or question is actually what happens if we select one of those scoring functions or those transferability measures to select just a model and then just perform hyperparameter tuning on the selected model. So this is what we basically call separated model selection and HPO. Basically select independently the model and then do the HPO. So for this, we try 3 different state-of-the-art transferability metrics. They are called LogMe, LIP, and NC. And we can see that even if these metrics, they are selecting a reasonable model, only selecting the model and then doing HPO is not enough. So QuickTune outperform this strategy because, of course, we have a large set of models and then we are allowed to change and look different models during the optimization. It's still an interesting observation is that LogMe is very competitive compared to the other 2 optimizations, but also the difference is quite large, especially for the extended version of the meta-dataset. So a practitioner might still wonder, okay, but why do I need all this QuickTune approach if I could basically just take a large model and do some parameter efficient fine tuning? So first, what we have to say, first, this parameter efficient fine tuning adds more hyperparameters, so we can easily like account for these new hyperparameters into our approach. So basically, we just need to extend the search space, but basically they are this parameter efficient fine-tuning are orthogonal strategies to our approach, and they can actually be combined. But in case a practitioner just really think that the parameter efficient fine-tuning on a large model is enough, we perform an experiment where we actually show that that QuickTune still is a good strategy, a better strategy. So what we did for this experiment was to select Dino V2 and just apply LoRa recomposition for updating the hyperparameter. So this is efficient because we just need to fine-tune a small set of parameters instead of the whole network. But still, we can see that the performance is not matching or outperforming QuickTune. But interestingly, for LoRa, we can see that for large datasets, the performance gap starts to close compared to small datasets, where probably there is some overfitting happening, I hypothesize. So also another strategy is linear probing. That in that case is basically fine-tuning the last layer and freezing the whole network. This is super efficient because then we just need to compute parameter the gradients for the parameters in the last layer, and we don't have to backpropagate and so on. So it is very efficient, but still we can see that it's not outperforming QuickTune. So For efficiency and performance, QuickTune is a better approach. So we also wanted to understand what happens if we actually delete the meta-learning component or the cost-aware component. So in all the experiments, we can see that the combination of cost awareness and meta-learning is important, but it's also interesting to see that the component that is more relevant is the cost awareness. So the green line is the one that has a cost, and we can see that the green line is still competitive, except in the standard version. And this plus C means that we have cost awareness, and this is the case of the green line, but we don't have meta-learning. And the G means that we are performing gray box optimization. So there is only one case where we don't perform gray box optimization. Basically, we use a GP that is not meta-learn and it's not using any cost information. And this is by far the worst approach, but still the combination of cost awareness, meta-learning gives the best performance. And we can see the meta-learning is especially important also for the extended version, because we can see that the gap between meta-learning and cost awareness is larger than the only cost awareness. It means that the gap between the green line and the blue line is larger in this case. So now for the conclusion, so we present an efficient method for fine-tuning architectures in model hubs, applying gray box optimization, meta-learning, and cost awareness. We created a meta-dataset that has more than 20,000 learning curves, and that we use to evaluate our method. We also demonstrated the effectiveness of our method by comparing it against different optimizers and also other lightweight alternatives, like using some parameter efficient approaches or selecting the model and then performing HPO. And then we can see from this work there are still many interesting research questions that we can answer. For example, what happens if we use a more complex acquisition function that is actually multi-objective, for example, accounting for the cost and for the performance, or we use cost cooling for the denominator in the acquisition function. Another very important venue or very important research question is how can we transfer this to other modalities, especially in NLP. This is a very important topic right now. So we are curious to see whether we can use model hubs in NLP to improve to improve the optimization, the hyperparameter optimization on them by accounting in all the models that we have in the model hub. And other interesting research question that I consider it could give a lift to the performance, or even it can be a completely orthogonal approach, is how can we actually select the one-star optimization, select the best initial configurations so that they are efficient. They are not only well-performing configurations, but also efficient. It means that it doesn't take a lot of time to perform one epoch. Because it might be the case that when we select one specific configuration, that configuration is actually super expensive, and then running only one epoch for one star in the optimization is even expensive. So it might be more interesting maybe to evaluate small data set, small models for warm starting, for example. So yeah, thank you. That's all. So now we can, if you have any questions, I'm very happy to answer them.
Thank you.